All right, folks. So today we're talking about section 4.1. And like I mentioned last time, if I recall correctly, chapter 4 is all about probability. And this first section is just probability, is just introducing some of our basic concepts and terms. So, of course, we start out with a whole bunch of vocabulary. First, there's a lot of talk in these sections about trials and experiments. These are both words for the same sort of thing, where it's a process that is repeatable with a random outcome. Right? So whether you win or not at a video game is a experiment depending on, or is not an experiment depending on what type of game it is. But for most games, it's not, because how well you play changes the outcome. Right? So a trial or experiment is something you can do over and over and over again. And what the outcome of it is depends, or doesn't depend on anything particular. It happens randomly. So sort of the stereotypical ones are flipping a coin, rolling a die, drawing a card. Those sort of things where the outcome depends on chance. Every trial has something called a sample space, and this is the collection of all possible outcomes. And another word we're going to use a whole lot is event. This is related to the sample space, and it is a collection of some possible outcomes. Right, so there is one sample space, which is everything that could possibly happen. Right, so if your trial is to flip a single coin, the sample space is heads and tails. Those are the two possible outcomes. If your trial is to roll a six-sided die, then your sample space is 1, 2, 3, 4, 5, or 6. Right? And if that's your sample space, right, so roll a six-sided die, then the sample space is 1, 2, 3, 4, 5, 6. At least that's one way to write up the sample space. The book does a couple with pictures, because really it's what happens on the top of the die that you're looking at, but that's sort of a good shorthand. And some example events, right? We might have the event that we roll an even number, right? Or we might have the event that we roll an odd number. Or we might have the event that we get a 2 or a 5. Or we might have the event that we get a number bigger than 3. Right? So there are a lot of other events, but those are just some events that can be in there. Now, that's just some vocabulary to start setting up what we're looking at. There's I think they present you 3 different types of probability, but the 2 that we're focused on are experimental probability and classical probability. And really, our focus is going to be on classical probability stuff, right? So for experimental probability, we have the probability of an event happening. Right, so this is the probability that the event E happens, right, is equal to F divided by N, where F is the number of times F happened, and N is the number of times you ran the experiment. Right. So we have a very similar thing for classical probability. Again, we're looking at the probability that E happens, right? So that's actually the same probability there. And they wrote it like this. All right, so N of E is the number of outcomes in E. N of S is the number of outcomes in S. Right? So really there's a reason why they use the same notation there. It's because they mean the same thing by that N of, right? And now the thing with experimental probability is that it's going to fluctuate based on how many times you run the experiment and what happens for it, right? So for an example, and this gives an estimate, right? Possibly a very good estimate, but it gives an estimate. So for example, if you have a non-weighted coin, you know that there's a 50-50 chance that you flip heads, right? So if we flip a coin, right, then the probability of getting a heads on the coin is 1, because there's one thing in the event, divided by 2, because there are 2 possible outcomes, right? So the event equals heads, and the sample space is it was going to be heads or tails. Now, experimentally, we're going to say I flipped it 10 times and got 6 heads. Right, then experimentally, the probability of getting heads is 6, because that's the number of times we got heads, divided by 10. Because that's the number of times we performed the experiment. Right, and so that's a decent estimate. And one of the nice things that we get in this section is that the law of large numbers says that the bigger n is, so the more times we run the experiment, the closer the experimental probability is to the actual probability. Right, so 10 is not a very big number, so we probably don't expect that small run of experiments to give us the exact answer, right? It's not really fair to expect exactly 5 heads when you flip the coin 10 times, right? But if you flip the coin 1,000,000 times, you should expect to get very close to 500,000 heads, right? 1,000,000,000 times, you should expect to get even closer to 500 million, so on and so forth. So one of the things that I probably should have said up here is this only works if all outcomes are equally likely. Right, so again, if we flip a coin, if we roll a die, if we draw a card, then provided we're not cheating and have a loaded set of die or a loaded set of dice or a trick card deck or a weighted coin, then all of those outcomes are going to be we are equally likely to get a 1 through 6. We're equally likely, turns out that's a hard phrase to say, of getting a heads or a tail. But when it does work, we get our exact probability that way. Let's see. So when we're doing this classical probability, one of the tricky things to do is to get your sample space, right? Because if you can find your sample space full of things that are equally likely, then you can you just have to count things and you're done, right? So one of the ways to do that is with a chart. So a chart for classical probability. Is we're going to have a setup where we're playing a game where we roll a 6-sided die, and if we get 1 or 2, we get 1 point. If we get a 3 or a 4, we get 2 points. And if we get a 5 or a 6 on the die, we earn 3 points. Right. So one of the things to stress here, for this to be classical probability, it's important that all 3 of those things are equally likely, right? So if we have this thought bubble here, if 1 gives us 1 point, and 2, 3, 4 gave us 2 points, and 5, 6 gave us 3 points, we can't do classical probability. Right? We'll be able to do that eventually, or at least something very close to it when we get to next chapter, but we can't do classical probability because it's not equally likely that we get any 3 of these outcomes, right? So just for the sake of notation, right, and these letters don't mean anything particular, I'm going to call this L, I'm going to call this M, and I'm going to call this H for low, medium, and high, right? So, whoops, I forgot one last thing about our game, which is we get to roll the die 3 times. Right? So the first time we roll the die, we can either get low, medium, or high, right? Those are our 3 options, and as we mentioned here, it's important that they are equally likely, right? Now, if we roll low on the first die, then the second die we could roll low, medium, or high. I'm going to run out of room very quickly. And if we roll high, we could also roll low, medium, or high on the second roll. Right, so this is the first roll. Get my eraser out real quick. This is one of the times it would be handy to have the fancier Apple pen. That's not what I wanted to do. There we go. This is the, I'll get it right one of these days. This is the second roll. And then the third roll, we get low, medium, or high again. And all of these different rolls man, I hope I'm going to be able to fit this. I wanted to do an interesting example, and this is what it gets me. Low, medium, high, low, medium, high. Whew, just barely fit. And then I have some absolutely abysmal straight lines. Right? So if we look at, for instance, what this guy says that we got low, low, low. Right? That's what this one did. So in other words, this is 3 points. Right? That's one way to look at it and analyze it. Right? So, first question that might come to mind is how many things are in the sample space, right? So if we count down here, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 21, 22, 22, 23, 24. There we go. That's what got wrong. 25, 26, 27. So we have 27 things in there. And what all of them are depend on the questions that we might want to ask, right? So maybe we want to ask, what's the probability that 2 of our rolls were high rolls? Right? So I'm going to put an exactly here. That can be pretty important. So exactly 2 of our rolls were high rolls. So we need to go through here and figure out which of these branches correspond to that. So I'm going to pick up a color so I don't have to draw this whole horrible chart over again. Right? So we want to know that 2 of our rolls were high rolls. So we notice that if we look down this path, right, if we focus on these, then if the first one was low and we have 2 highs, then we have to go high and then high to get the 2 highs, right? So that's one outcome that gives us 2 highs. Same as if we start at medium up here. If the first one is medium and we get 3 rolls and we want 2 of the rolls to be high, well, the only way for that to happen is to go high and then high again. Right? So that's our second outcome in this particular event. So now this one is the tricky one, right? So we notice that if we start off high, it's possible that we went low for our second one, but then we would have had to have gone high again. Right? So we pick up that guy. If we started off going high, right, starting over again, if we started off going high and then went medium, that's allowed, but it means we had to have gone high again for our second one. So we've got this guy. All right? Now, we could have also, again, resetting, we could start off high and go high, right? But then we've already gotten our 2 high rolls, which means either low or medium is allowed. Right? So we could have either had the second 2 be high, which is what we get these 2, or we could have the first 2 be high, in which case it doesn't matter what the last one is, or we could have the middle one be something else, and it's the first and last one that are high, which is where we get these 2. So if I'm counting it right, we've got 1, 2, 3, 4, 5, 6. So we've got 6 outcomes in that event, and we've got 27 things in the sample space total. Right. So another question we could ask is, what is the probability of scoring exactly 3 points? Right, and that's still going to be a 27 on the bottom because our sample space is still exactly the same. We've got 27 different ways it could all go down. So we just need to count up which of these got us 3 points. Right, and so again, if we think about going here, this gets us 1 point to start with. Right, so if we already have 1 point and we want to get 3 points, then going to H is not allowed, right? Because that would get us 4 points total, and that's too much, right? But we can go to L and to M from here, right? L would have gotten us another point, so that would have left us at 2. M would get us all the way up to 3 points, but then there's nothing down here that we can get to. Right? Any of them would get us more than 3 points, right? So that doesn't actually lead anywhere. But if we have 2 points, we're allowed to earn 1 more point, so we pick up this event, or that outcome, as being in our event, right? Now, I think we're going to have a similar problem here, right? In this case, we start off with 2, which means that a second roll of high and a second roll of medium is right out off the bat, right? Because a second roll of high would get us to 5, second roll of medium would get us to 4, and that's too much, right? So that means that going down to here is the only possible one at this stage. But then once we get to here, we've gotten our 3 points, and rolling anything would get us more than 3 points, right? It would get us 4, 5, and 6 respectively. So none of those get us exactly 3 points, right? And it's going to be even easier now that we're up here at high. We get 3 points from this guy, which means that we're not allowed to roll the dice anymore if we want to stop at 3 points, right? So it turns out there's only one outcome in that event, that very first one that we calculated. So the probability of scoring exactly 3 points is 1 out of 27. Right. Now, we don't always have to make one of these charts, right? So if that's complicated and annoying to you, don't think like that's the only way we can do probability, right? We could also say, suppose we have 15 black socks, 6 white socks, 3 blue socks, and 2 red socks. And they're all jumbled up, mismatched in our drawer. And for some reason, we like to play a fun game where we reach into our sock drawer and draw out a sock without looking at it. So, let's say our first blind draw was a white sock. So now we're going to ask, so what are the odds of getting a matching pair with another blind draw? So really this is asking for the probability of drawing a white sock. Right? If we've already drawn one white sock, then getting a matching pair means drawing another white sock. And so this is going to come down to the number of White Sox divided by the number of Sox in total. Right? But one of the things you need to be careful of when you're reading word problems like this is to make sure to take the whole problem into account. Right? So if I just look at this first sentence, that's telling me there's 15 plus 6 is 21, plus 3 is 24, plus 2 is 26. Right? And so maybe at first it seems like we should have a 26 there. But if we read the whole problem and look at this second sentence, it says that we've already picked a white sock out of the drawer. And presumably, if we're trying to get 2 socks to wear, we're not going to put that sock back in the drawer. Right? So really, there's not 26, there's 25. Right? Because there were 26 before you started this whole process, and you took 1 out of that pile, so there's 25. Right? Similarly, the number of White Sox, if we just read that first sentence, it looks like 6. But obviously I said the word similarly already. If we look at this second sentence, then we know that we've already pulled one of those White Sox out of the drawer. Right? We own 6 White Sox, but one of them is already in our hand. Right? So the number of White Sox we have left to choose from is only 5. Right? So we get 1/5. Right? And so one of the differences between these problems is that in this first problem, we got a process for how this works, right? We're actually doing something with repeated trials. And we'll talk a little bit more about that later. But the description of this was a process was the description of a process, right? Down here, our second problem was the description of a situation, right? So this first sentence did sort of, in a way, list out our outcomes from the very beginning, right? So this first process, or this first problem, is the kind of thing you need to do when you are in charge of building the sample space, right? The second problem is an example of what you do when someone tells you what the sample space is right off the bat. And so that's sort of our initial overview of probability. We're going to come up with some fun and exciting rules for what to do with and or statements in our next section. But I will see y'all then.